Hi guys, today we're going to be talking about part 2 of biogeochemical cycles. To recap, last time we went over the major biogeochemical cycles, chemical reservoirs specifically in terms of the carbon cycle, greenhouse gases, photosynthesis and respiration, decomposition and oxidation versus carbon burial, how we can track carbon burial and oxidation events throughout Earth's history using carbon isotopes, how we can use the relative difference in inorganic versus organic carbon isotopes to track these changes, and a couple of the ways that we can use the tool of carbon isotopes in diverse areas of research, like for evidence of early life on Earth and life on other worlds, as well as tracking the cause of current climate change. But today we're going to be talking about mountain building and weathering as a carbon sink, carbon and sulfur burial and anoxia feedback mechanisms, and ocean chemistry, specifically magnesium to calcium ratios, chalk formation, silica, and how all of these mechanisms relate to one another, even though on the surface they may seem like they're very different from one another. So let's jump right into mountain building and weathering. You might not know that tectonics has played a huge role in affecting climate throughout Earth's history. Plate tectonics can cause mountain building events, which can cause an increase in weathering, which can cause a carbon sink or burial of carbon, because the weathered carbon that is transported to water bodies like the ocean can end up in limestone, which can then be buried. The buried limestone can then be transported to a subduction zone, again through plate tectonics, and then the subduction can cause melting and expulsion of this carbon from a volcano, again releasing it to the atmosphere as carbon dioxide. And so as we can see, this is a cyclic process, and this is what we call negative feedback, which is something we defined in the last video, where we have one trend leading to something that causes the opposing trend to occur to balance out trends in climate change. Here I have an example of negative feedback in which maybe you have an increasing temperature regime caused by an increased carbon dioxide concentration in the atmosphere, and because of this warming you get increased precipitation rates, which will cause increased chemical weathering rates, and increased weathering increases the sink of carbon or reduces carbon dioxide in the atmosphere, which will decrease the temperature and cause the opposite temperature regime as what we had in the beginning. This feedback mechanism is a negative feedback because it's a balancing act. And I want to point out here that weathering is an important factor controlling the current warming trend. In fact, weathering is thought to have prevented so far a runaway greenhouse effect. And you might think that with all this negative feedback, how could we ever have a runaway greenhouse effect? Well, there are a lot of negative feedback loops operating throughout biogeochemical systems. However, there are also what's called positive feedback loops. Positive feedback is something we also defined in the last video, in which we gave the example of ice. Melting of ice due to warming can cause a decrease in surface reflectivity of Earth, and therefore an increase in absorption of solar radiation on Earth, and therefore more warming. This compounding effect, rather than balancing effect, is called positive feedback. And positive feedback is what causes runaway climate change in either direction. However, since we've already talked about that in the last video, and we've already discussed here how weathering can act as a carbon sink, now I want to switch gears and talk a little bit about carbon and sulfur burial and oceanic and anoxic events. This is another example of feedback, and you may think it's really different from what we just talked about, which was tectonics and weathering, but it's actually all related. As we'll see at the end of this lecture, I'll bring it all back together and show you how all of these factors that we talk about in today's video can affect one another. But for this section, we're going to talk about anoxic events and how underlying biogeochemical feedback mechanisms are causing the onset and termination of these anoxic events. So first, I want to bring your attention to the figure on the right. What we have here is a depiction of an oxic water body regime where we have plenty of oxygen, as shown in the green box of the oxygen reservoir in the water body, which is causing a lot of respiration of organic material, which is causing abundant CO2 to be available for photosynthesizing organisms, which then convert the carbon dioxide back into sugars and back into organic material that aerobic respiring organisms can then reoxidize again. This is the photosynthesis respiration loop we talked about last video. But there's also a lot of other things included on this figure that I need to explain to you before we go into how these systems will be affected during the anoxic event. So another thing we can see here is that some of the organic material that's being produced by the primary producers at the surface of the water body is going into organic carbon burial, as we can see with this really skinny arrow. And this arrow is very skinny because the majority of organic matter is being reoxidized, and this is why these two photosynthesis respiration arrows are the biggest right now. But as you'll see when the anoxic event starts, as I'll show later, this organic carbon burial barial arrow will get a lot thicker. And that's because when you have oxygen depleted regimes or anoxic regimes, you will allow that organic carbon to escape oxidation and actually become buried. And so keep an eye on that arrow as we move through this anoxic feedback mechanism. Additionally, some other things we have on this figure include this sulfate reservoir here that's so far completely full, and we'll see how that might get depleted during the anoxic event due to what's called MSR or microbial sulfate reduction. And then microbial sulfate reduction leads to pyrite burial. Pyrite is a mineral made of iron and sulfide, the reduced form of sulfur, and this iron sulfide mineral becomes buried as more sulfate is reduced. And so we'll see as the anoxic regime occurs that this sulfate reduction will take hold and deplete this sulfate reservoir and cause increased pyrite burial. And later we'll see why that may lead to the termination of the anoxic event. The last couple things you see on this slide are the iron and phosphate reservoirs over here, but I'm not going to talk about those quite yet. I don't want to confuse you with too many variables at this point. So now we're going to run through this feedback loop once while just focusing on the carbon dioxide, oxygen, and sulfate for now. And then we'll come back to why phosphate and iron become important later on. So here's a lot of text on this slide, but don't worry, we're going to walk through this step by step. Like I already mentioned, the regime shown on this figure so far starts with a high O2 concentration and a high carbon dioxide concentration. At some point, you might get a shift of balance in this photosynthesis respiration cycle due to this huge carbon dioxide reservoir maybe causing an increase in primary production or photosynthesis that shifts that cycle out of balance. And this primary production increase will cause the onset of anoxia, because as we get all that organic material building up in the surface ocean and creating this detrital organic matter that's raining down and starting to bury organic material at the bottom sediment, the organisms that respire that organic matter are using up all the oxygen to do so. And in doing so, they're creating an anoxic environment in the deeper parts of the water. And once anoxic, this allows for the burial of organic matter. As we can see, these arrows have now become huge as the anoxia has taken over the bottom waters of this water body, and this allows for organic carbon to escape oxidation and become buried. An additional effect that we see is this sulfate reduction arrow becoming huge, as well as pyrite burial. This is because that sulfate reservoir is now becoming used by sulfate reducers who are reducing the sulfate into sulfide and burying it as pyrite. This is because sulfate reducers operate in anaerobic environments without oxygen. And so as they're taking up all the sulfate, they're causing pyrite burial to build up. And then the anoxic event only lasts so long before you get its termination and an eventual return to the normal oxic regime. This is because as carbon burial acts as an oxygen source to the atmosphere, you will eventually get so much oxygen that builds up, you will reoxidize those bottom waters. Additionally, you have carbon dioxide depletion, which slows down primary production long enough to allow things in the photosynthesis respiration cycle to become balanced once again. And this causes an increase in oxygen, a return to oxic regimes, and an increase once again in carbon dioxide. Now, another really important reason that this anoxic event was terminated in this case is the sulfate depletion during the anoxic event. Like we said, during anoxia, sulfate becomes depleted due to microbial sulfate reduction, and that builds up the pyrite burial. However, once you run out of sulfate, the sulfate reduction stops and pyrite burial stops, making iron more available to sequester phosphate. This is really important because phosphate is a major nutrient that when it becomes depleted or limited by something else sequestering it, like in this case the iron, it limits the primary productivity long enough to contribute to the termination of that anoxic event. This is also the reason that nutrient overload can cause ocean anoxia. For example, in some continental margins today, we have river runoff that contains our human waste, fertilizers, etc. in it that causes an over-nutrifying effect in that continental margin area, causing an anoxic environment in the bottom waters of that continental margin. And you might have also heard the term hypoxic. It's a similar concept. It's just depleted oxygen rather than no oxygen. And so these hypoxic or anoxic conditions today are caused by nutrient overload, which is a similar effect to nutrient limitation causing oxic conditions. So now I want to show you the YouTube video that I got these diagrams from because I think it's a really helpful animation to run through now that we've explained the concept behind all of these feedback mechanisms that are operating in the system. So I'm going to show you this video and just remember how we went through it, how it's going to happen. The anoxic event will happen and then it will terminate. And what I want you to pay attention to now is actually the right side where you have temperature fluctuation and carbon isotope composition of inorganic carbon. We talked about carbon isotopes last time and how an increase in carbon burial will cause a positive carbon isotope excursion in inorganic carbon material during periods of increased carbon burial like anoxic events. So we'll keep an eye on the timing of these carbon isotope excursions through this anoxic event as well as how that affects temperature. So let's take a look. So as we start with a fully oxic regime and then it starts to become anoxic and carbon burial begins to occur. This is when you get the huge jump in carbon isotopes and a huge drop in temperature. And then you start to come back to the regular regime by the processes we talked about that terminate that event, and you bring temperature back to normal and carbon isotopes back to normal as well. So this is all I wanted to show for this anoxia feedback concept here, and I hope that this helped you a little bit understand how carbon and sulfur burial can affect redox conditions and chemistry in the ocean, and how this can affect the rock record isotopically, geochemically, so that we can go track these types of events throughout Earth's history. And in doing so, we can reconstruct paleoclimate, but also better our ability to project future climate regimes and fluctuations by furthering our understanding of how these biogeochemical feedback mechanisms and cycles change Earth's climate. So switching gears once again, now we're going to discuss ocean chemistry in terms of skeletal mineralogy. So here we'll talk about mainly magnesium to calcium ratios and skeletons and shells and what that can tell us about ocean chemistry throughout Earth's history, how we can track seafloor spreading and sea level throughout Earth's history, how one group of organisms invented a whole new rock type at one point in Earth's history, and also a little bit about silica in chert sponge spicules, diatoms, and radiolarians. So let's jump right into magnesium and calcium ratios and calcium carbonate material. Basically, shells and skeletons in marine organisms are often made up of calcium carbonate, and there are actually two mineral types that have the chemical formula calcium carbonate. These include aragonite and calcite. The composition of these two minerals is the same, calcium carbonate, but the difference between these two is their mineral structure. Basically, their mineral lattice is stacked differently, which causes different ions to be able to substitute for the calcium ion and calcium carbonate differently in these two different minerals. There are many ions that can substitute for calcium in the calcium carbonate mineral structures of aragonite and calcite. However, we're going to focus on magnesium for the purposes of this video. Magnesium substitution in carbonate minerals occurs because it has a similar atomic radius size to calcium in its ion form. However, because of its slightly smaller ion size, it likes to fit in calcite more than it does in aragonite. Aragonite has a mineral structure that favors larger atomic radius sizes to substitute for calcium in its crystal structure, whereas calcite favors smaller atomic radius sizes. And so because magnesium substitutes for calcium only in calcite and not in aragonite, during periods where the ocean's chemistry has had a high magnesium to calcium ratio, high magnesium calcite and aragonite are the dominant calcium carbonate minerals that precipitate, whereas during periods where the ocean's chemistry has had a low magnesium to calcium ratio, normal calcite precipitates. So we can track this throughout Earth's history, but now you're probably wondering, why does it matter? What are we able to tell by tracking the magnesium to calcium ratio of ocean chemistry? Well, this has to do with what controls magnesium to calcium ratios. And this has to do with seafloor spreading at mid-ocean ridges. Mid-ocean ridges are basically just divergent plate boundaries where plates are drifting apart from one another, causing magma to come up and form new oceanic crust right there. This newly formed crust allows seawater to circulate through, and as seawater circulates through this newly forming crust, you get ion exchange. Ion exchange at spreading centers causes seawater to lose magnesium content and gain calcium content from the basalt that is circulating through. This loss of magnesium and gain of calcium causes the magnesium to calcium ratio of the seawater seawater at this spreading center to decrease. This means that periods during Earth's history where seafloor spreading rates were high and the overall volume of mid-ocean ridges were high, that magnesium to calcium ratios in the ocean during this time were likely very low, whereas times where seafloor spreading is relatively slow, you get higher magnesium to calcium ratios in the ocean. So now we know that we can track seafloor spreading rates using magnesium to calcium ratios and calcium carbonate minerals, which is already pretty cool. But there's another thing that we can tell using these ratios and carbonate minerals, and this is sea level change. You might be thinking, how is sea level affected by mid-ocean ridges? Well, in this depiction, we can see that the overall volume of mid-ocean ridges at a fast spreading ridge is much greater than the overall volume at a slow spreading ridge. And this volume increase increases sea level as a whole. And increase or decrease in sea level can also affect other major biogeochemical cycles, as we'll show in an example later. But basically, the gist that you should get out of this magnesium to calcium ratio section is just by analyzing the chemistry of calcium carbonate minerals, we can reconstruct not only oceanic crust production rates, but also sea level change throughout the geologic past. So now that we've gone a little bit through ion exchange and calcium carbonate minerals and how that can tell us a little bit about ancient conditions on Earth, let's get into the organism I mentioned earlier that basically invented a whole new rock type. Biology can also play major roles in altering ocean chemistry through Earth's history. For example, during the Cretaceous, calcareous nannoplankton, or coccolithophores, shown here in the picture to the bottom, began to majorly dominate the ocean environment and formed huge fine-grained calcareous deposits of the rock that is now called chalk. The rate at which chalk was accumulating got up to 1 millimeter per year, which may not sound like a lot, but that's a crazy fast sedimentation rate if we're talking in geologic terms. But how is this possible for them to start creating chalk at this crazy fast rate? How come they didn't do it before? They had evolved earlier than the Cretaceous, and why was it now that this was their most prolific time in Earth's history? Why didn't they continue to deposit chalk at this rate? Why was it just during the Cretaceous? Well, it all comes back to the magnesium-calcium ratio chemistry that we were just talking about. Magnesium to calcium ratios in the ocean during this time were at an all-time low. They were at the lowest they've ever been throughout the entire Phanerozoic. This enabled calcite to precipitate easier than it ever had. And so this is a prime example of how chemistry affected biology, and then biology affected geology and chemistry. And so all of these systems are just so wonderfully intertwined. And here's an example of a major chalk quarry in England, and this just shows how extensive the Cretaceous chalk deposits can be. Now I want to talk a little bit about silica, and this is the last thing I'll talk about before we go to the last slide, where I will hopefully bring all of the concepts of biogeochemical cycles together that we've talked about and show you how they all relate to one another. So in terms of silica, this is another prime example of how biology has majorly affected ocean chemistry throughout Earth's history. For example, before about 100 million years ago in the mid-Cretaceous, silica would precipitate directly from seawater to form a mineral called chert. However, after 100 million years ago, this no longer was possible. Organisms that built their tests or skeletons with silica began diversifying and proliferating so much that they extracted nearly all the silica from the ocean, and it was no longer available to precipitate directly from seawater. These organisms include minorly silicious or glass sponges, but the major contributors to the extraction of silica from seawater were diatoms and radiolarians, which are again microorganisms like the calcium carbonate coccolithophores that we just saw on the previous slide about chalk. And this is another prime example of how these micro or nano organisms can really heavily affect biogeochemical cycles. It's important to note, however, that chert still forms today. It's not that this mineral was totally wiped out. It's just that now it's primarily a biogenic process rather than forming abiotically. So now I'm hopefully going to connect all of these things we talked about together so that you can better understand how these systems interact with one another. Here we have an animation of a mid-ocean ridge spreading, and I want to point out, if you remember, the seawater that circulates this newly formed crust that's coming out of this mid-ocean ridge is causing an increase in calcium and decrease in magnesium, causing the magnesium to calcium ratio to overall decrease. And in doing so, you get an increase in calcite precipitation relative to a aragonite. Additionally, the spreading rate increase at this mid-ocean ridge causes an increase in the rate of plate movement, causing an increase in the rate of subduction, causing mountain building, causing increased rate of weathering, which causes a carbon sink, which causes an oxygen source, which then causes the feedback loop we talked about earlier with the carbon burial anoxic feedback, where oxygen will increase enough to the point that things become oxic again, and you no longer have the anoxic event and no longer get the carbon burial, and then you have this loop occurring over and over again. However, I also want to point out that the things we've talked about in these past couple videos about biogeochemical cycles are not as simple as they may seem. I tried to simplify it enough to where you understand some examples of feedback mechanisms, but that does not mean that these are the only feedback mechanisms operating in nature. Earth is such a complex system, and you have to understand all of these things can affect multiple systems. It's not only one right after another. These aren't linear events. It's very sporadic and scattered and very confusing, which is why climate models are so hard to make. Additionally, I want to point out the components in Earth's system as a whole that may kick off these feedback events can be different. For example, like we show in this example, you have a change in the GEO or lithosphere causing the rest of these feedback mechanisms to kind of occur as a chain reaction type situation. However, you might also kick off some major chain feedback mechanisms by starting with a change in the hydrosphere, for example, another major Earth system, which includes the ocean, glaciers, rivers, lakes, frozen methane hydrates. For example, you might have frozen methane hydrates begin to melt due to slight warming, throwing the entire system out of balance because you get this positive feedback mechanism in which methane stored in frozen hydrates is released, and then that causes even more warming due to the greenhouse effect caused by more methane in the atmosphere, and this is a positive feedback mechanism. And that can kick off a whole host of other feedback mechanisms like we've talked about within these biogeochemical cycles. Additionally, you might have something in the atmosphere change drastically, causing a chain reaction of feedback mechanisms. For example, when ozone first began accumulating and stabilizing in the atmosphere, yes, ozone wasn't always around in Earth's atmosphere because oxygen wasn't always around, but when you had it first start to form, it changed all the other Earth systems forever because it changed the way in which biology could evolve because there wasn't so much intense radiation at the surface of Earth, and it changed the geosphere and hydrosphere. It changed everything, and so that can kick off a bunch of feedback events. Additionally, you have the biosphere, which we know throughout Earth's history has thrown a bunch of curveballs because we just talked about the appearance of chalk due to that one tiny microorganism, and we talked about the removal of silica from basically the entire hydrosphere, causing the termination of chert formation directly from seawater. Additionally, I've talked about some of my other videos, the Great Oxidation Event, where you had photosynthesizing organisms evolve and begin to proliferate so much that they changed the entire chemistry of the atmosphere, which then changed the chemistry of the hydrosphere and the geosphere and so on, and you get these major changes in one of these spheres, if you will, and then it kicks off all these other changes in the others. And so again, I'm just trying to explain to you how complicated these systems really are and how intertwined they all are with one another, so that I can emphasize to you that there's a lot of factors that go into this. It is not simple, but with this, I want to emphasize to you that that's why Earth history is so important. I know I'm yelling and I'm sorry, but this is so important to me that I can get this concept across, because that is the point of all my videos, is to explain how important studying Earth history and reconstructing Earth's past is in the general scheme of things, because by using our knowledge of how all of these systems interact with one another and have interacted with one another throughout Earth's history, we can understand what that has caused in terms of climate, so then maybe today we can understand better our current climate situation and make better climate models and predict more accurate climate regimes, and maybe understand how to operate in the future a little bit better so that we don't throw anything out of balance again. Anyway, I hope you guys enjoyed this topic as much as I do. I will for sure be coming out with more biogeochemistry videos in the future. This is one of my favorite topics, as you can probably tell, and I'm really excited to hear if you guys have any suggestions for future videos in terms of biogeochemistry, because this topic to me is just the coolest thing in the world. So anyway, with that, thank you guys again for joining, and I'll see you guys next time. Bye!